Hello everyone, welcome to Engineering Explained channel. In this session, I am going to take Basic Thermodynamics Model 1, Lecture 12. In that, I will take heat and work. Already in the previous sessions, I have taken the details of the work transfer. That is a form of energy, and heat is also a form of energy. And details of that heat I am going to take in this session. I will take the heat transfer means what? Its sign convention, the different types of heat like specific heat, sensible heat, and latent heat. The details also I am going to take. First, we'll take the definition of heat. Heat is defined as the form of energy, as already we know, that is transferred across a boundary by virtue of a temperature difference. Due to temperature difference, heat energy transfer takes place. The temperature difference is the potential or force for the transfer of the heat, and heat transfer per unit area is the heat flux. The transfer of heat between two bodies in direct contact is called conduction. If the two bodies are directly contact, then where the heat transfer is taking place, that is called as a conduction. The example for this one, the heat transfer through the solids where the molecules are direct contact, that is called as a conduction. Heat may be transferred between two bodies separated by empty space or gases by the mechanism of radiation through electromagnetic waves. Heat transfer takes place, and this is called as a radiation heat transfer. The example for this radiation heat transfer is the heat transfer from the sun to earth. That is the best example, because beyond the atmosphere, earth atmosphere, there is empty gas, vacuum is there, there is no gas also, and through that one heat is transferring by the radiation mode of heat transfer, and that is by the electromagnetic waves. The third method of heat transfer is convection, which refers to the heat transfer of heat between a wall and a fluid system in motion or within the fluid. From the wall to the surrounding fluid means for surrounding air, the heat is transferring by the convection mode, by the molecular motion heat is transferring. And within the fluid also, from the one location to the another location, heat is transferring, and that is by the convection heat transfer. Then further moving, the direction of heat transfer is taken from the high temperature system to the low temperature system. So we know that from the higher temperature region to the lower temperature region, heat is transfer, the heat transfer is taking place. That is the driving force or a potential for the transfer of the heat. And here we'll take the heat flow into a system is taken as positive, and the heat flow out of a system is taken as negative. The symbol K is used for heat transfer. That is the quantity of heat transferred within a certain time. Heat is a form of energy in transit. Energy in transit, like work transfer, both are energy in transit. It is a boundary phenomenon since it occurs only at the boundary of a system. Across the boundary, heat transfer is taking place. Energy transfer by virtue of temperature difference only is called heat transfer. All other energy interactions may be termed as work transfer. Okay, by the temperature difference, what energy transfer taking place? That is the heat transfer, and remaining energy transfer, what are there? All those are work transfer. Here is the sign convention. Heat transfer to a system is taken as positive. Okay, to a system, heat transfer we are going to take as a positive. Heat transfer from the system is negative. Okay, exactly opposite to this one, work transfer. Work transfer from the system is a positive, and work transfer to the system is negative. We have taken. These are the sign convention. One sign convention, if you know that one, other sign convention usually we can know. These are the during the experiment, the scientists are taken this one as a positive and negative sign conventions. And here the work output, the positive if you remember, then all other sign conventions we can recall easily. Here is the work transfer and the heat transfer in the form of the PV and TX diagram we are going to represent. The area under the curve PV curve is taken as the work transfer, area under the Tx curve is taken as the heat transfer. And here this is W122 is equal to integration of 1 to 2 PdV, that is the work transfer. Q122 is the integration of 1 to 2 TdX is the heat transfer. Just like displacement work, the heat transfer can also be written as the integral of the product of the intensive property T and the differential change of the an extensive property say x. Intensive property means which is independent of the mass. The temperature is the independent of the mass. And extensive property which is dependent on the mass. Here the unknown property x is taken and that x we are going to define later. Q1 to 2 then it is given by integration of 1 to 2 dq, that is equal to integration of 1 to 2 t into dx. It must also be valid for a quasi-static process only. This is valid for only quasi-static process. And the heat transfer involved is represented by the area under the path 1 to 2 in EX plot, as already in the previous slide we have taken. Heat transfer is therefore a path function. Heat transfer is depend on the path followed during the process, therefore it is a path function. That is the amount of heat transferred when a system changes from a state 1 to state 2 depends on the path the system follows. Similarly, both work and heat transfer are path functions. Therefore, dq is an inexact differential. Now, dq is equal to pdx where x is an extensive property and dx is an exact differential. Okay, therefore, dx is equal to 1 by t dq, and this to make q integrable, that is an exact differential, it must be multiplied by an integrating factor, which is in this case 1 by t. The extensive property x is yet to be defined. It has been introduced in chapter 7 and it is called entropy. The entropy we are going to take in the further chapters. Next, the other types of heat are we have to discuss here. The next one is the specific heat. The specific heat of a substance is defined as the amount of heat required to raise the temperature of a unit mass of substance through a unit degree. Here, to increase the temperature of the unit mass of a substance for 1 degree, what amount of heat is required, that is called as a specific heat. The symbol C will be used for specific heat. Then C is given by C is equal to Q by M into delta T, where Q is the amount of heat transfer in terms of joules, M is the mass of the substance in terms of kg, and delta T is the rise in temperature in Kelvin. Next one type of the heat is sensible heat. The sensible heat is defined as the amount of heat required to raise temperature of water from ice point to boiling point temperature at at a given pressure. Here, concerned to the water, we have taken the sensible heat. Okay, it may can be applied to the any other fluids also. But here the for the water to increase its temperature from the ice point to the boiling point, what amount of heat is required? That is called as a sensible heat. And here, ice point temperature for the water is 0 degrees Celsius at atmospheric pressure, and boiling point temperature is the 100 degrees Celsius. To increase the temperature from 0 degrees Celsius to 100 degrees Celsius, what amount of heat is required? That is called as a sensible heat. The next one is the latent heat. The latent heat is the amount of heat transfer required to cause a phase change of a unit mass of substance at constant pressure and temperature. Here we should keep in mind temperature also. Here the unit mass of any substance if you take, its phase should change. To change the unit mass of that substance phase, what the amount of heat is required, that is called as a latent heat. And we should know that one, what are the different phases of the substance? The phase, solid, liquid, and vapor phase of the substance are there. And as we know that there are three phases in which matter can exist: solid, liquid, and vapor, or a gas. And from solid to liquid and liquid to vapor, during that, or from vapor to liquid or liquid to solid, the phase change what it is there. During the phase change, what amount of heat is required, keeping the temperature constant. The temperature does not change here, and keeping that temperature constant, what amount of heat is required, that is called as a latent heat. Then the latent heat are again classified into three types. One is latent heat of fusion. The heat of fusion is the amount of heat transferred to melt unit mass of solid into liquid or freeze the unit mass of liquid to solid. To convert the unit mass of a substance from solid to liquid or freeze it from the liquid to solid, what amount of heat is required, that is called as a latent heat of fusion. The latent heat of vaporization is the quantity of heat required to vaporize a unit mass of liquid into vapor or condense unit mass of vapor into liquid. Okay, to vaporize a unit mass of liquid to uh, vapor and the condense a unit mass of vapor into a liquid, that what amount of heat is transfer taking place, that is called as a latent heat of vaporization. Last one, latent heat of sublimation is the amount of heat transferred to convert unit mass of solid to directly vapor or vice versa. That means vapor to solid directly. What amount of heat is required, that is called as a what amount of heat is required or transferred is called as a latent heat of sublimation. These are the different types of the four heat are there. The heat, generally the heat transfer by the temperature difference. Next one is the sensible heat and latent heat and specific heat. These are the four types of heats we should know. If the common definitions and the understanding if we have, then there is no confusion in the heat transfer. Thanks for watching. If you like, share, subscribe, and comment.